This video is going to cover the basic requirements to design specific transmission line values, and we're going to focus on the requirements for a Wilkinson power divider. So if we take a look at the basic values for a Wilkinson divider, we see that there are two types of transmission lines: Z0, or the default impedance, and Z0 times the square root of 2. So we are going to go through the process to design Z0, which is 50 ohms, and Z0 times the square root of 2, which is about 70.7 ohms. So with that in mind, we'll close this and start working on the transmission lines. First thing I'm going to do is create a new schematic, and I'll just call this transmission lines. What I'll do is place microstrip lines, and the basic element is M line or microstrip line. We drag that into the schematic, place it, and then we'll put 2 ports on it. And control right click to flip it left to right. So here is our basic setup for the 50 ohm line. You can see that we're going to adjust the width, and the ports are both 50 ohms. So what we're going to do is adjust the line to give us a perfect match to these ports. Now for the 50 ohms times the square root of 2, we're just going to Control A to select everything, Control C to copy, Control V to paste, and we'll use this second setup for 50 ohms times the square root of 2. So in order to match this line to a different impedance, we need to adjust these Z equals 50 ohm values. Now I could calculate what 50 times the square root of 2 is, but there is something that you should be aware of that's built into the program that is extremely useful. So I'm going to click the Help menu, Contents and Index, go to the Index tab, and I'm just going to type EQU, and I want built-in functions. We can see that if we scroll down, there is a square root function. So square root of X. And this is how it is specified: SQRT and the value in parentheses. So with that in mind, we'll come back here and we're going to select both ports simultaneously. So we click on one, and we hold the Shift key to click on the other, double click on either one, and the Z value we are going to specify as 50 times SQRT 2. And when we say OK, you can see that both ports have been adjusted to that value. And that means that now when we match this line to these ports at a perfect match, the line will also be 50 times the square root of 2. So these are our two lines. The other thing that we must have to fully define these is the substrate definition. So the easiest way to place that is to simply right-click on either one of the transmission lines and add model block. And this posts M sub element. And I'm going to set this up to be FR4. So the value here is 4.45. We're going to go with a 20 mil substrate. The thickness of the metal will be 1.4 mils, which is 1 ounce copper. It's 1 ounce per square foot, and it is 1.4 mils thick. The rho, the conductivity, is normalized to gold. So for copper on a PCB, we're going to specify rho as 0.7 because copper is a better conductivity is in gold, and the dielectric tangent is going to be 0.0031. We do not need to deal with ER nom because this only functions with electromagnetic analysis, and we're not going to do that in this example. So this is set up now. Just a couple of more things we're going to set up. Options, project options, and I'm going to define the frequency range from 2 to 10 gigahertz, 0.1 gigahertz steps. So we'll click apply. This is now our frequency range. Let's say OK. And I am going to create a graph. And for matching, I'm going to create a Smith chart. You'll see why in just a minute. So here's the basic Smith chart, and I'm going to add 2 measurements. So I'll right-click on the graph, add new measurement. And what we want is port parameters, S, that's the default measurement. The data source name will be transmission lines, that's the name of the schematic. We want S11, add, and S33. And 33 because these ports are 3 and 4. So we're just going to look at the match to port 1 and port 3. So we can now put these next to each other and look at both windows. Window tile vertical, and here we go. So now, if I run the analysis, we can see these are our values. Now, the key here is both of these plots are on the left of the center. And with a Smith chart, that means both of these lines are lower impedance than the target. So we are going to adjust the values of these lines, and we're going to decrease the width, because decreasing the widths will increase the impedances, and that's what we're going to do. So let's select both of these lines, double click, and I'm going to make the width tunable. And I'm going to set the constraints from 10 to 50 with a step size of 0.2. And 50 is our default where we're starting. 50 mils, 50 mils. And you can see that both of these turn blue to indicate that they're tunable. So now that I've defined everything, let's start by looking at the 50 ohm line. And I'm going to open the tuner. That's this slider toolbar button. You can see the tuner for both of the lines, transmission line 1 and transmission line 2. So for 50 ohms, we're going to adjust transmission line 1. And as I adjust this, you will see S11, the blue curve, starts moving closer and closer to the center, and the diameter gets smaller and smaller until it literally becomes near 0, a dot. We will now do the same thing for the 50 times square root of 2. You can see it gets narrower, but both of them become literally a dot. So now I am holding the control key and zooming in on this, and we can see they're not perfect, but they are literally right in the center. And when a line is properly designed for the desired impedance, the frequency doesn't really matter. It's always the desired impedance. So both of these lines are now set. 50 ohms is 36.6 mils, and 50 times the square root of 2 is 18.6 mils. And that makes sense. A narrower line is a higher impedance, and this is the higher impedance. So these are the types of things that you can easily do to design transmission lines with desired impedances. For more tutorials, visit us at resources.ema-eda.com, and don't forget to like and subscribe to our YouTube channel.